Well, ladies and gentlemen, good evening. And what a terrible shame that I have to interrupt these conversations. A veritable hubbub of pleasant discourse, and it's great to have you here. Distinguished guests, we have many of those in the room tonight, and our fellows, great fellows and associates, and our friends as well. Very warm welcome here to the Royal Academy of Engineering for the 2024 Hinton Lecture. And of course, we are delighted to say that we're also welcoming our viewers, and I suspect there will be a couple of hundred anyway online, who are watching our live stream from all over the world. So just before we begin, just some service announcements, if I may. Some housekeeping notes for all of you, please, here at Prince Philip House. Of course, we've not been informed of any scheduled fire drills. If the alarm does go off, then please follow our academy staff. There are also several academic staff here as well. But if there are any requirements, please follow our staff to the nearest exit. In addition, please, as always, colleagues, please turn your mobile phones to silent for the duration of the lecture and the Q&A session. However, do keep your phones to hand, because we'll expect you, if you are so minded, to post about the event on social media. And you can also see our hashtags on the screen, and you will need your phones later this evening to submit your questions, which I will moderate and pose to our guest speaker. Because for those of you who are new to this special occasion, it is in fact the Academy's flagship annual lecture, named after the late Lord Hinton of Bankside, the first president of our Academy, or the Fellowship of Engineering as it was called then. And the subject of our lecture this evening on energy and climate change is highly appropriate, as many of you will appreciate, as Lord Hinton led the construction of Calder Hall in Cumbria, the world's first commercial nuclear power station, which opened almost 70 years ago. The Hinton Lecture was created as a forum to discuss how engineering and technology can help solve the greatest challenges of our time. And there is no question, colleagues, that getting to net zero greenhouse gas emissions is the challenge of our time. And it's been my top priority during my 5 years as President of the Royal Academy of Engineering. During that time, of course, and what we've been doing recently, I was able to join in COP26, and the Academy was active during COP26 in my hometown of Glasgow, where 130 countries came together to commit to net zero targets. During that time, I had the great honour and privilege of welcoming former President Barack Obama onto my campus, who spent a half day with us to inspire and challenge climate scientists and engineers, and particularly young activists, to get out there and do something. And the last two words he pleasantly shouted to them as he rejoined his cavalcade to go back down to the COP26 site was two words: get active. And I'm sure we'll hear that in spades from our guest speaker tonight. We must model, we must talk, we must plan and strategize, but we need to be much more active about dealing with this major challenge of our age. But here at our Academy, we've provided critical advice to government, both national and devolved governments, on how to build a more sustainable society. Our National Engineering Policy Centre has advised on how to identify and make confident decisions about actions that we can take now that will put us on the path to net zero. Actions, of course, like helping people reduce their energy consumption, providing more charging networks for electric vehicles, of course, and the grid infrastructure, and investing in research and development to evaluate new and innovative technologies such as green hydrogen. You should be interested also to know that with funding from the Gatsby Charitable Foundation, we have just embarked here at the Academy on a new study on rapid decarbonisation of the GB electricity grid. And we've also just opened a major new programme to support some of the most exciting innovation in decarbonisation and sustainability. Announced by the Prime Minister in late 2023, the Green Future Fellowships will offer grants of up to £3 million to develop practical breakthrough technologies and scale-up solutions to achieve net zero. This is what the Academy is all about: great research, innovation, and then moving to solution. But of course, none of this is possible without our fellows. The Academy brings together the brightest and the best engineers and technologists, both here in the UK and internationally. And of course, that includes our esteemed speaker, who is indeed one of our international fellows. And our speaker is a truly unique individual who has his very own Venn diagram, both as a physicist and engineer, pushing the boundaries of scientific discovery, and as a government policy maker, aware of the limits of what national and global politics can deliver. He won a Nobel Prize for Physics for his work on methods to cool and trap atoms with laser light, and, as you know, he served as the United States Secretary of Energy from 2009 to 2013. President Obama paid tribute to him, and I quote, "He has a unique understanding of both the urgent challenge presented by climate change and the tremendous opportunity that clean energy presents to our economy." So, colleagues, we are absolutely delighted and honoured to welcome to this stage Professor Steven Chu, the William R. Keenan Jr. Professor of Physics and Professor of Environmental Science and Engineering at Stanford University. And I'd like now, just as we have a short video, to invite him to deliver his lecture on the challenges in getting to net zero greenhouse gas emissions. Please welcome to the stage our 2024 Hinton Lecturer, Professor Steve Chu. Thank you.
The Royal Academy of Engineering harnesses the power of engineering to build a sustainable society and inclusive economy that works for everyone. It's working to solve the greatest challenges of our time, including how to decarbonise energy sources to slow climate change. The Academy's Chair in Emerging Technologies, Professor Susan Gourvenec, leads on intelligent and resilient ocean engineering. Her research looks at how technologies such as robotics, autonomy, sensors and big data can help increase renewable energy supply from the oceans, so that these technologies can create new engineering processes that are more efficient and cost-effective. It will enable us to scale up ocean development economically, with less environmental impact and with reduced risk to workers. For example, pre-installation site surveys for offshore development usually involve large, specialist ships with up to 40 people on board. Through research like Susan's, smaller vessels, fewer people offshore, autonomous systems and machine learning methods can be used to gather the data. Once installed, monitoring offshore structures traditionally involves inspection by people. This becomes increasingly impractical and risky as many more structures, typically operating without a crew, are installed. However, Susan's remote monitoring systems could relay continuously updated information, creating living designs that self-diagnose problems. By supporting this research, the Royal Academy of Engineering is supporting the responsible, sustainable, and economic use of ocean resources.
I am really delighted to be here and to talk about this. And so let me just get on with it. I will add also, there will be a couple of slides on nuclear in this talk. Okay, so a little bit of data. Number one, there it is. So this is the mean global temperature from 1850 to January 2024. And you notice it just went over 1.5 degrees. So the 1.5 degree goal is no longer there. We know that this is due to human activity. In particular, it's due to greenhouse gases, carbon dioxide, methane, N2O, others. But those of you also know that the climate's changed in the past. We have this geological record that it went up and down many, many times. If you look at the last warm period from this current relatively warm period, it was about 1.5 degrees warmer than it is today. From the fossil record of the critters that live in the border of land and ocean, the seas were about 6 to 9 meters higher on average. So that's not a model, that's called history. But it's not only carbon dioxide. 30% of greenhouse gas warming is due to methane. And another significant part that we see rising in the future is N2O. That's not 30% warming, that's a misprint. It has a 100-year lifetime. It's 300 times worse than carbon dioxide. We're beginning to see changes in weather, heat floods, fires, droughts, water shortages. This is water stress areas. The World Bank has made an estimate, perhaps 200 million climate refugees by 2050. So you are well aware of maybe 10 million refugees going into Europe. It's completely changed politics. Imagine 200 million. So this is something you should pay attention to. This is a projection. So this is climate models, large uncertainties in these models. On the x-axis is time, 1990 to 2100. On the y-axis is the carbon emissions, greenhouse gas emissions equivalent that we're doing today. Where are we now? We're here. We're somewhere between no policies and current policies that put us somewhere between 2.8 and 3.2 degrees centigrade. So that's significantly higher than the last ice age, which is 6 to 9 meters higher. Okay. The y-axis is very important because this is zero carbon emissions on everything. And that is very, very difficult. And the other danger is that people who have done any snorkeling or scuba diving know that you start to go deeper in the oceans, few meters to 2 and 4 kilometers deep. The bottoms of the oceans are about 2 degrees centigrade. Very, very slow mixing between the surface and the bottoms of the ocean. So think of this as huge ice cubes keeping the Earth warm. So even though we put this greenhouse gas layer, energy coming in after you average the solar cycles, constant. Energy going out, less. But we're warming up the ocean. And we will not know for 50 years, maybe 100 years, what the effect is of what we've done today. Is this, you've been smoking cigarettes for 20 years, you stopped 30 years ago, and you've started a chain reaction of mutations which will give you heart disease, stroke, lung cancer, COPD. And so this is one of the great dangers, is this delayed reaction. Okay, so this is globally what things come from. This is an IPCC summary. You see industry, buildings, you know about electricity and heat production, transportation, you know about airplane travel, about 2%. And so getting to net zero greenhouse gas emissions is not going to be easy. It's not just getting rid of greenhouse gas emissions from electricity generation. Lots of it come from steel, concrete, plastics, chemicals, textiles. That's got to go. And you've got to get rid of the entire greenhouse gas emission coming from the food supply chain. And we don't have the technology now. And I'll discuss more about this. This lecture is going to have a bit of history. And so let me remind you, those who don't study history are doomed to repeat it. This is well known. Yet those who do study history are doomed to stand by and helplessly watch while everyone else repeats it. Here's an anxious woman asking, what's going to happen to me in the future? And she gets the answer. You will make the same foolish mistakes you've made before. Not only once, but many, many times again. Okay, so here comes some history. James Watt improves the Newcomen steam engine. First application was pumping water out of coal mines. But this was part of what led to transition from human and animal power and horsepower, for example, to horsepower. Other thing, materials inventions. This is Henry Bessemer. And steel was invented long, long ago, but he invented one of the first processes to make it scalable and efficient enough. Why did he do this? When did he do this? He did it as a wartime effort. And during the Crimean War, 1853 to 1856, the explosives were breaking the cannons the British had. So he invented a way to make steel commercial. Okay, what was the Crimean War? Well, it was Russia invading Crimea, and Europe saying, no, 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 we don't want to do this. History. Okay, everybody's aware of the transistor, and the invention by Bardeen and Bertin of the so-called point contact transistor, totally impractical, but they finessed it, and this is legendary. William Shockley wasn't on the first transistor patent. He was their department head. He was incensed. He was really mad. He actually marched both of them into the office and said, sometimes the people who did the work are not going to get the credit. And so what he did is he holed up, and he was a genius, condensed matter theorist. So he holds up and he's going to summarize quantum mechanics and what we know about solids based on quantum mechanics. And for 2 or 3 days in this hotel room, he laid down the foundation of semiconductor electronics. So he deservedly shared the Nobel Prize. But what you may not know is the thing that really made the transistor and semiconductors important was the ability to purify silicon to parts per billion and way below that, 10 minus 10. And this is Bill Fan, who invented zone refining. You take this hunk of dirty germanium, you heat it up and you let it slowly melt, and you go back and forth and the impurities are driven to the edges. I was a young starting scientist at Bell Laboratories in 1978. There was this old guy, totters in an office next to mine. He stays there for a couple of hours and totters out. Some people visit him. And finally I asked my department, who's that guy? He said, you don't know who he is? I said, no. He's Bill Fan. He invented zone refining. It was that established semiconductor electronics. So he gets to do whatever he wants to do. And he says, he goes on and says, this reminds me of these 2 young cavemen. They watch this old guy go, and he says, who's that guy? The other young caveman says, you don't know who he is? He invented the wheel. The other young caveman says, yes, but what has he done lately? Also invented this single seed crystal, first germanium and then silicon. So it's these 2 inventions that actually made it practical, and it could go to industry. Charles Kao gets the Nobel Prize for optical fiber communication. Without the ability to make ultra-pure silicon, this would have gone nowhere. It was materials. The great inventions were going to the physicists, as they should, but but they should have also been going to the materials people. Okay, so solar, great progress in solar. This is recent history. In 1910, $378 a megawatt hour, plunging by 1919 to this price. Still going down, down, down. Since the beginning of silicon photovoltaics, which was discovered at Bell Laboratories, the price has fallen by 98-point-something%. Okay, it's like amazing. But there's a new renaissance going on that's I'm very happy about. And these are very complicated materials called perovskites. On the upper left-hand side, you see structure of this. And over here, you see the rapid progress of the time going here, very rapidly growing up. This is solar cell efficiency. University of Oxford, one of the leaders in perovskite research. But the problem was the perovskites were more or less weeks or months. 2 groups within the last couple of years have achieved accelerated life testing of more than 15 years. It's going to go to 20, 25 years. This is thin film technology, energy inputs to make this stuff really cheap. This could transform solar yet again. So it's very, very exciting. Anyway, okay. So we've seen marvelous industrial revolutions, several of them, but we'll need a 4th industrial revolution to power this carbon-free economy. The fact that the levelized cost of solar in places where there's good sun, maybe not London, but is less than the cost of natural gas in most places in the world. But it's got to get 2-fold less expensive, and same with wind. Wind is also done very well. Wind, by the way, is more dominant than solar in renewable energy. But it has to be much less because the full real cost means enhanced transmission distribution systems, backup generating capacity, and energy storage. So transmission distribution systems, very big deal. So now this is over here, planned high voltage DC transmission lines. You need DC in order to go underground, undersea. AC will just couple to the conductors too well. So these are planned under construction. This is a solar atlas of the average solar energy that hits Europe and Northern Africa. This is not being planned, but being discussed. Perhaps we can have some lots of solar in cheap land, desert land, and go to Europe. There's a problem. There's energy security issues, and I will touch upon this. Okay, the transmission lines do not use copper. They use aluminum. Aluminum is not as good a conductor, but it's lighter weight. Right now, they mostly use a steel core because the steel provides the strength. The aluminum doesn't have enough strength to support the cables as you go from pylon to pylon. Now being engineered are carbon cores, which are lighter and stronger. And then they anneal the aluminum and space fill it. So that's a big deal. The highest voltage lines today are in China, 1.1 million volts, 12 gigawatts. 3,200 kilometers. This is about 5% of the energy. So this is part of some exciting things. Now, if you talk about engineering, then you have to talk about materials. And so being me, I guess, doesn't have anything to do with physics, you want to step back and look at what are the materials we have on Earth and what are the materials we use on Earth. And so in this red thing, you see in terms on the y-axis is plotted annual world production in metric tons of stuff we pull out of the Earth. What is it led by? Concrete, followed by oil, coal, natural gas, and iron ore. Then asphalt and cement, then wood. Then there's a whole bunch of drop where you get to aluminum, copper, zinc, all the way down. All this blue stuff in here, that's plastic. But the plastic feedstock is oil and natural gas. Okay, so most of what we drag out of the Earth, a large fraction of it is fossil. All right? And then there's glass and bricks and other things. And so we have to be very conscious of this. And is there a way to use this carbon to start to replace some of these other materials? Is there a way to make a carbon conductor that's better than copper and aluminum? Well, we actually know that carbon nanotubes are much better than copper and aluminum by a couple orders of magnitude in conductivity, but it's too expensive. It's all about money. And so another engineering challenge. Another thing that we're doing, these are forecasts of what energy we spend on communications, networks, consumer devices like television, computers, mobile phones. Green is data centers. In 2010, about 2% of electricity, but by 2030, the expected case scenario is 20.9%, 21%. It could be worse. It could be over 30%, or it could be much better. And I should also say that half of compute technology today in the world is in crypto mining. And this is not fully appreciating what is happening in machine learning and the energy sink of machine learning. The NVIDIA chip is 700 watts, the A100, going to a kilowatt, and racks going to 100 kilowatts. But you're having rooms full of these racks. Okay, so we got to do something about that. And in my humble opinion, I know the good arguments for cryptocurrency, but the first application, and remains the highest application, is money laundering. So anyway, I wish it could be outlawed. There is a new kid on the block, in terms of computation. The driver is CMOS technology, dominant, and like silicon photovoltaics, it's been, never underestimate silicon. Nevertheless, there are new materials based on process again, and if the older people in the audience are maybe old enough to remember these magnetic core memories, they send 2 wires, and then you can magnetize this. You magnetize it, it remembers what it is. You change the state, magnetize it the other way. So it's a logic 0 and 1 that doesn't need any more power. Today's DRAMs, for example, is a capacitor, it's a charge, but it leaks, so you have to have a transistor to keep it charged. So your memory, not the memory sticks, but the ones that are used in compute consume power. And so these things are promising. There's a couple of companies forming. A person I recruited from Berkeley to come and work in the Department of Energy to lead the solar, what we call the Sunshot. It was a friend of mine, Ramesh, and he's a co-founder of Kepler Compute, which is trying to commercialize ferroelectrics. It's not only going to be good for compute memory, but it also can be used in logic. So whether it works or not, we don't know, but we need a new technology. Order of magnitude, where CMOS will end up. Okay, very important. You only need 100 millivolts, and you want to switch it, and you remain switched. So this is a big deal if it works. Energy. This is something that's a little weird. 2008. I get a call, and President-elect Obama, this is like the 3rd week in November, he said, he'd like to talk to you about a very important job. I said, I don't really want to work in government. And he said, no, you shouldn't. He said, well, okay, what job? Secretary of Energy. Okay, I'll fly to Chicago and talk to him. So I go to Chicago, I'm at the 15th floor of some rented space, and he walks in, he doesn't have a tie, he doesn't have a jacket, and the room is hot. It's like 78 years. Okay, he's from Hawaii. Okay, and so he comes in and says, everybody's telling you you should be the new Secretary of Energy. I say, who are these future former friends of mine? He ignores it, and so we just talk for an hour. How do you feel about this? How do you feel about that? And he was trying to figure out whether we would be compatible, and I was trying to figure out whether we would be compatible. My wife, Jean, is in the front row, so she just called me when I said, this guy's really good. If he asks, I will say yes. The previous president wanted to get me interested in being science advisor, and I said no for a number of reasons, but mostly, there were a number of reasons, but the most important was being an advisor is different than having budget control. So if you have $60 billion a year, it's a very different position. So I started calling on the phone scientists and engineers I knew. This, by the way, has never been done in the past, and it has never been done going forward. And I said, come join me. You wouldn't believe I would work for the government. Come join me. It'll be great. Arun Majumdar, Ramesh, a bunch of other people, a couple dozen people. And then we together called up other people. And so the number of people in the National Academy of Science and Engineering, 6 during this time. There will be at least another 6 in the future. So imagine this, working for a government. Okay, you need an active scientist who's willing to get on the phone to call his friends in science and engineering. Okay, so let me tell you about energy storage. This is my favorite battery. Let me tell you how it works. When you have renewable energy, you do the energy intensive thing, and then you've got stored energy. Okay? So pump storage is 95% of all energy storage. Okay, so this is too fine print, but I'll just read it to you. Leading list in pumped storage. What's pumped storage? You take water below a dam and you pump it uphill. The turbines are very efficient. And you can pump up, if you got 30 meters, you pump up, you let the water come down. You said, this is not good, there's a lot of friction losses. No, 75% efficient. As good as a flow battery, 80%, okay? So China leads the way, United States second, believe it or not, Japan is third, and others. Okay, so I was very encouraged that the Federal Energy Regulatory Commission, which permits these things, got applications to make pumped storage in the United States grow by about twofold. You might ask, what's China doing? It used to lead, it still leads, of course. So here's China. Where does it end? Okay, China goes from 34 gigawatts. It's power and energy, both are important, but this is power, to 270 gigawatts. So it will be much more than the rest of the world combined. Okay, and so that's an important thing. But pumped storage requires expanded transmission distribution systems. Not all places have mountains. So you need other forms of storage. This is a plot of energy on the x-axis, energy per unit weight. On the y-axis, energy per unit volume. That's the Tesla batteries. I think it'll be here in 10 years. This is good. This is not a prediction because I'm on the board of a battery company that's sending out samples like this. It will take 6 years before anything, and it's got to be cheap enough to be mass produced to get into a car. But nevertheless, it's good. Cost is great. Energy is money, and cost is everything. And so the cost of batteries has been plunging. In 2000, the cost of the lithium-ion batteries, before it was large-scale production, $2,000 a kilowatt hour. 20 years, $100 a kilowatt hour. 2030, probably less than $50 a kilowatt hour. So this is called the learning curve. The more you produce, the better you get. The more you produce, the better you get. It's not a law of physics, it's not a law of economics or engineering or anything, but it's true for whatever reason. It's true of the Model T over a 20-year period. It's true of lots of technologies. A few of them it's better, like the cost of sequencing DNA. But you can ask, will there be a materials situation? If it's lithium, is there going to be enough lithium for EVs? And the answer is, well, actually, maybe. So Chung Lu was a postdoc of mine, and he was a graduate student in East Way at Stanford. And we started working on the extraction of first uranium out of seawater, and then lithium. And she's now an assistant professor at the University of Chicago. And what she's found is that she can start from seawater, lots of seawater, and you get to 8-to-1 lithium, which this is great. Batteries, lithium metal sulfur battery could be theoretically highest energy density, but it has a real problem because it grows dendrites. And so we are trying to develop a way of being very conductive to lithium to keep the dendrites from forming. And so this is very exciting. Hydrogen, very, very big deal. Colors of hydrogen, gray hydrogen, methane. You turn natural gas into hydrogen, you vent the CO2. It's not better for the environment, and its costs, depending on how much natural gas costs, say in the United States, $1.50 a kilogram. Blue hydrogen, where you capture and sequester the carbon dioxide, maybe double in price or 80% in price. Green hydrogen, very much more expensive because it uses very expensive renewable energy. There's a new color of hydrogen. It's called white hydrogen. It's produced primarily in the earth by natural causes. Hydrogen comes out of the ground. And so if there are rock formations like natural gas rock formations that keep it trapped, you can then mine hydrogen. Preliminary costs of companies looking into this now, 50 cents to $1 a kilogram. If this turns out to be true, it's going to really transform the world. Mined hydrogen. So it can either be in natural seepages or you inject water into iron rock, change the oxidation state, and out comes hydrogen. I don't know whether it's going to work, but it's getting a lot of attention. Hydrogen, very important to decarbonize steel, plastics, chemicals, fertilizer, aviation fuel. Our current electrolyzer is not really good. And finally, hydrogen, very leaky and impossible to detect spectroscopically. Not impossible, you need femtosecond lasers at a very high order non-linear process. You need a way of sensing hydrogen leaks, and there is not a good spectroscopic signature, and so the question is, what do you do? Right now it's a mass spectrometer. Can you miniaturize it? But there's a better idea coming along. You let hydrogen interact very selectively in a chemical reaction, and you detect a chemical reaction this big. It's this big, you can put it on a drone. Before you can detect hydrogen pipelines, before you have hydrogen pipelines, you need to detect leaking hydrogen. Because if it goes in the upper atmosphere, it keeps methane there longer. So it's like a greenhouse gas. Electrolyzers, precious metals, there are PEM electrolyzers, there are solid state electrolyzers, and here is a picture of Bloom Energy. Ravi Prasher, another person I recruited to come into Bell Labs, and now he then became associate lab director at Lawrence Berkeley, and he was lured away with a multi-million-dollar per year salary to work at Bloom Energy. He sends me an email a couple of months ago and says, we got 88.5% thermodynamic efficiency. Electricity to hydrogen or hydrogen to electricity. So you can send hydrogen by wire and produce it where you need it at the site. Okay, a big deal. And so, and lifetime was a problem. You're beating that. So I'm very optimistic. Of course, we eventually want to take CO2 from the atmosphere, from other CO2 emitting sources, combine with clean energy and water to produce hydrogen CO and make liquid hydrocarbon fuels. Why? It's because this is a crude oil tanker, and how much does it cost to ship and store crude oil halfway around the world? And the answer is 2 cents a gallon. This is a transcontinental transmission line of energy. And so big push to figure out a way of getting hydrogen in a form that you can put on a tanker. Okay, moving along. Even with all this stuff, we will need a turn-on compact source. And there are going to be two choices in the future. It's going to be fission with spent fuel disposal or nuclear reactors. Let me make very quickly. I'm running out of time. I promised them 35 minutes. I don't have a heart attack. We'll go a little over. This is deaths per terawatt hour led by brown coal, lignite, then black coal, then oil, biomass gas, hydropower. Where's nuclear, including Chernobyl? It's down here. It's a little bit safer than wind. Why is wind dangerous? Because people fall off the towers. And it's a little bit more dangerous than solar, but wait, it's 100 times safer than burning wood pellets because of the particulate matter. Okay, people are scared of radiation. This is a very complicated graph, but the background radiation, apart from, don't get a lot of CT scans, that's a lot, but dental x-rays are pretty inexpensive. But of natural occurring radiation, a reasonably high fraction of that radiation we receive is in food we eat. Okay? Think about that. This is in your body. And there's naturally radioactive foods. Brazil nuts are the worst. Bananas, carrots, potatoes, red meat. So to make it more understandable to the public, there's a new unit of radiation. It's not a sievert or millisieverts. It's called a BED, banana equivalent dose. And so if a banana is 1, carrots are 1, lima beans are 1, Brazil nuts are 2, red meat is 2, beer is not quite up there, it's 0.3. So anyway, I don't have time to talk about fusion. We can have a question and answer period, but big breakthrough. The question is whether it will become commercial. We don't know. My personal estimate, which is also the estimate of the person who actually pulled off the laser fusion of Livermore, he's a friend of mine, is greater than 40 years and never. Somewhere in between there. Having said that, should we invest in fusion research? Absolutely. The problem is so big, this is a pittance. Okay, so anyway, moving right along, we need a fourth agricultural revolution because of all the greenhouse gases. History, lesson, this is present time, going back. warm period, cold period, warm period, cold period. This is the 6 to 9 meters higher, 1 degree warmer than we are today. But agriculture didn't start just in the Fertile Crescent in the Middle East. It started in North and South China, New Guinea, Ethiopia, Americas. Why did it take so long? This is Homo sapiens. The brain over here was as big as it was when agriculture started. So let me zoom in this. The climate stabilized enough so you could have agriculture. And with stable agriculture, you can create wealth, so you could have kings and you can have physicists. Okay. A third agricultural revolution, started actually by the president of the British Academy of Sciences. He set over a race. Can you get nitrogen, ultimately fertilizer, ultimately from the air and nitrogen? And Fritz Haber gets the Nobel Prize in 2018 for the Haber-Bosch process. It was an oversight, so the Nobel Committee corrected this. In 1931, he gets the Nobel Prize for the Haber-Bosch process. They had to think of an excuse. The excuse was for the invention of high pressure, high temperature catalysis, which was the Haber-Bosch process. Another important aspect, Norman Borlaug, plant breeding. And with plant breeding, he could get very productive wheat and could withstand irrigation fertilizer. That third agricultural revolution took us from 3.1 billion people to 7.9 billion people. This thing down at the bottom is the land used in agricultural production of cereals. Did not increase. Cereal production went up. This was amazing, okay? Greenhouse gas emissions from things we eat. That's beef. It's the worst. Poultry and meat is 10 times better. You know, you're better off eating tofu, but not everyone likes tofu. Or wheat or bread or things like that. Annual emissions of carbon in the world, if beef and dairy cattle were a country, they would exceed the greenhouse gas emissions of the United States or the EU plus Great Britain. Okay, so you need to think a little bit about this. Bioengineering, if you put all the human mass and the animals we eat on one side of the scale and every other mammal on the other side of the scale, we're 96% of biomass of the Earth. We have geoengineered the Earth. Now, we're likely to grow to over 550 parts per million, and we need to capture carbon. We're emitting 52 gigatons a year. We need at least 10 or 20 gigatons. We want to remind you of the scale. We produce 2 billion tons of landfill waste a year. To store 20 gigatons, we'll need 30 to 40 times the volume storage per year of landfill waste. Okay, this is a non-trivial problem. We have automatic carbon capture from plants. It works great. Growing trees is great, but they saturate. And so, you know, it's beginning to occur to us in foul land with less fertilizer and water, can you grow biomass to just sequester it? Okay, here, besides forests saturate after 20, 30 years. What about wooden buildings? You grow a forest for the wood structure to replace the steel and concrete, and if you don't tear that building down but keep it up for a long period of time, hundreds of years, old London is wooden buildings up to 1,000 years old. This is really carbon sequestration that's better than forest, because you use the new trees, you know, leave the old trees alone to grow the wood to do this, but it's more expensive than steel and concrete. Another, but not that much more. A little bit of policy and a little bit of engineering. Okay, so conclusion, I want to leave you with this. How much time will it take to make this transition to carbon-free? Will happen in 2050? Well, again, history. We went from wood to coal. 1850, coal was started to produce in mass. This is 1960. Then we started to go to natural gas and petroleum conversion. Winston Churchill getting STIPs, liquid fuel. And now you see in the pittance up, a little hydroelectric, nuclear, renewables. That's one way of looking at history. 60-year transition, okay? Let's look at another way of looking at what's happening. This is 1800 to 2019. You don't see this transition because the Indonesia, India thinks, China still is, even though China is the biggest, marching full speed, so you have coal, oil. We just added to the energy. Okay, so let me conclude. I think we are collision past 3 degrees. Imagine the Titanic and those 2 young sailors up in the crow's nest looking, is that an iceberg? And saying, I'm not sure it's an iceberg. It's an iceberg 20 years. Is it really there? No, it's not there. And then clang, 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 we're hitting. And then remember the scene, they go to the engine room, reverse engines, hardcore, turning left. And they were saying, turn, damn it, turn. It takes at least a half a century to turn. Okay? So I gave a talk when I was in the Department of Energy, Titanic, the sequel, and I was told by my political minors, you can't talk about that. But yes, we should. It's 37 minutes. I'm stopping.
Well, ladies and gentlemen, a tour de force, and I can only say that I'm so proud of our international fellow of the Royal Academy of Engineering, who is clearly a systems thinker, a wonderful physicist, but also a systems engineer. Because you'll see we have a QR code, which I think is about to appear on the screen here. Please, I have some questions here which I'm going to start to pose to Steve. We'll have about 15 or 20 minutes for us to consider. I know Steve is quite keen to respond and engage with the audience. If you could pose your questions on Slido, and you will see these appearing. Those that you wish to upvote, that you would like us to escalate to pose to Steve, do that too, please. But I know there'll be many questions, Steve. We'll have a reception shortly after our session here. You may have a chance to speak to Steve. But let me begin with posing a question from one of our participants, if I may, Steve. And Gautam asks the question that global greenhouse gases levels, and I should say very sobering, but the data that you have presented us tonight shows this is not fanciful. This is the direction of travel that we're on, sadly. But the greenhouse gases, Gautam says, will not come down sufficiently by 2050. Even the UK has to build at least 35 nuclear power plants of 3 gigawatts to shut down aviation, livestock and farming. So he poses the question, should we not focus on adaptation to make societies more resilient to future impacts of climate change?
I think you have to focus on both mitigation and adaptation. Adaptation absolutely necessary. The sea level rise will occur, but that's the least of it. I'm worried more about water supply and agriculture, and agriculture wiping out local farming and the 200 million potential refugees. But adaptation, definitely. We're trying to adapt plants and breed them to drought tolerant, things like that. In nearby, the U.S. Armed Forces was my biggest advocate when I was in D.C. Well, because naval bases are kind of near the water, and but there was a deeper reason. When there's instability, there are wars, and then they would see young men and women going to war and dying. And so, yes. And adaptation is really strengthening the local economies. So you can do your best to weather the storm.
Good. Thank you for that. There's a political undertone to this guest speaker, so you may choose to move on to a more technical question. But Sarah asks the question, what could Trump possibly winning the US election mean for the energy transition?
I founded an agency called RPE, it stands for Advanced Research Projects Energy. It was designed to have risk-taking. Government funding wanted to take no risks. And we wanted 9 out of 10 projects to fail, but they had to be ambitious enough. I kept on saying, we don't want singles, we want home runs. And so when Trump became president, he zeroed out RPE budget every time. But even though it's Republican Congress, they kept on increasing the budget. And he said he will end the war in Ukraine. That's true. He will apply U.S. support. And that would end a lot of things. And so this would not be a good thing.
It reminds me of one of our Academy's mantras, Steve, that systems approach needs us to understand the complex interaction between technology, policy, economics, society, and any one of those being disruptive, kind of an untold impact on the other. Bcash is asking what your views might be on small modular reactor technology as an option. We've talked about fusion and the challenge in that journey, but SMRs?
Yes, so SMRs, they vary from, and we'll talk about in terms of electricity equivalents, the big nuclear reactors, 1 to 1.6 gigawatts per reactor. We're talking a couple hundred megawatts down to below 50 megawatts. The economy and scale is in large reactors, so you try to make them an economy in number. It's good SMRs. You can make them have enough heat capacity to use total control of water, electricity, water cooling, everything, not to melt down. When I was Secretary of Energy, I funded 3 companies in the US to do engineering with the requirement, no real possibility of a meltdown. You need a couple hundred orders to get something going. Yeah. Now, having said that, it's not going to help us in time. There's a long lead time for anything nuclear. And so we've got to do everything else. So it's like waiting for fusion and then just going on with life. So I do have hope for it, yet to be proven. We've forgotten how to build nuclear reactors on budget, on time. We have to relearn that. They've gone up about 8-fold. When it was originally in the 80s, the cost was absolutely fine. Hinkley is, over budget. So we have to relearn how to do this. But these can be made in a factory at scale.
I think this next question, Steve, was inspired by your very encouraging reflection when you were the Secretary of State for Energy. You brought together the scientists and engineers as a group. But Luke asked the question, Steve, how might we as scientists and engineers do better to ensure that policy and political decisions reflect the current state of scientific knowledge, especially and particularly on issues like climate change?
Well, there's a couple of things. I was a Secretary of Energy. I started quoting Sheikh Yamani, a former oil minister, and he said the Stone Age did not end for lack of stones, and the oil age will not end for lack of oil. He's absolutely right. You used to poke a hole in the ground 5%. Now you're expecting 50% of a reservoir. You've gone up in order of magnitude. The ability to find oil and gas is getting better and better. It's getting as fast an ability as solar and wind. Yep. And so, these are things that we really have to be aware of. Okay, so I'm not sure I really.
No, that is good, and that might be other discussions we'll have later on. You pointed and you mentioned Steven.
Okay, let me
please.
So Sheikh Yamani, what did he mean by the oil age is not going to end? You go to better solutions. You don't look on the ground and see a bunch of rocks and say, if it weren't for those politicians, we wouldn't have these stranded assets. So scientists and engineers have to come up with better solutions being economic competitive solutions.
Good. Okay. We've talked about, and you've seen in our slides, we talked about Europe, America, China, India, but we have a question from our audience. How might we engage with developing countries on the delivery of net zero goals?
I think first, I'm a big believer in helping them mitigate and adapt. There's a revolution going on with solar. You saw it with your eyes. We need the same issue with energy storage. There are going to be a lot of places they're going to be off-grid and remain off-grid, but it's too mountainous, not enough people. And so these technologies are very important, and we've got to help them. Right now, the default is fossil fuel. India is very receptive. Indonesia is not. They're just scraping coal out of the ground, and because it's known technology. And I think we have to help them economically with this. And anywhere where there's an opportunity where it's competitive, cheap capital, major problem, issue. And so you need international or backup to ensure cheap capital.
I remember being in a few lively sessions at the Glasgow COP26, Steve, where this capital issue was raised, and there seems to be great enthusiasm in the investor community, but the conditions and the longer term ROI needs to work for them.
Yeah, the thing that they tried to crucify me several times, no, not several times, during my whole time when I was the Secretary of Energy, was we made a loan to Cellular that went bankrupt. The project was chosen by career people in the Bush administration. It was the first on the list. They knew about it, but it was politics. So once I had to go before an oversight committee, and there they keep you on the stand for 4, 5, 6 hours. And so I asked the chief of staff, can at least, if they're going to crucify me, use clean nails? But anyway, the loan program was one of the most successful things because we were investing in billion-dollar projects Wall Street would not touch. And then when the program stopped, the financial community tripled the investment. It was a smashing success. We kept Tesla from going bankrupt. We helped GM develop their hybrid Volt, Nissan for the Leaf. And so this was money, cheaper capital.
Yeah, indeed. It's very often said, and I can subscribe to it, the cheapest and cleanest form of energy and the lowest cost of kilowatt hours is the one that we don't use. So David in the audience has asked us the question, do you see a major role for behavioural change in reducing emissions, or is it primarily down to technology development that we're going to solve this challenge?
Depends on how old you are. If you're in your 80s or 70s, many of you, I hope you'll be willing to change. But the younger people are beginning to think, do I really need a car? Do I really need to have a home with a yard and a garden? Or can I be willing to live, in a smaller apartment near the place I work so I don't have to waste an hour 2 hours each day commuting? So that's me. If you like meat, fine. But chicken, pork is much less than beef. Now, having said that, all of a sudden I notice, I shouldn't eat beef, and all of a sudden steak is tasting. We eat much less of it. But anyway, so habits can change, have to change, and people have to appreciate when you cook and boil water, put a lid on it. Yeah. And don't put it all the way up to see the gas spilling out of the edges. These are small things. Full dishwasher, full wash machine load, right? Try to use not a dryer, but okay. And then maybe in the last little bit of drying, then you can hang it up, okay? And so these are habits. So it really can start with personal habits. Indeed. And to teach people that this really matters.
We've got time for a couple more questions. There's clearly some fans of fusion in our audience, Steve, that won't surprise you. But one question that's been upvoted by quite a few is that you were clear you were, I was going to say pessimistic, but let's say pragmatic about when fusion might appear. But have you any ideas how we might accelerate this? Is there anything particular we could do to drive forward that potential for fusion?
I'm talking about commercial. I'm not talking about scientific fusion. I think either will work, but commercial. Commercial means capital cost risk. You think nuclear reactor at 10 billion, 15 billion, you're behind budget on that. Fusion will be much more expensive. And so, but the real killer is the materials problem. The neutron damage problem has not been solved. And that is the crucial problem of neutron damage. And so again, once you begin to concentrate on all the aspects. Another non-trivial thing is tritium. We don't have enough tritium to turn on either yet. And so this is another issue that you have to think about. How do you bootstrap up to get the tritium you need in fusion? So there are a lot of issues. I have a joke, but maybe we should save it at the end, or maybe you want it now.
Let us not keep you, please.
I reiterate, I'll say it again, we should keep on fusion. The question was acceleration, and I think the materials problem for commercialization is, in my mind, one of the most crucial problems. I have great faith in physicists to do the things. Just came back from a review of the Helmholtz, the Stellarator, the thing was that it turned on within less than a year after it was built, and we're hearing progress report, and they're accelerating their landmarks, and they're ahead of schedule. It's fantastic, but it will boil down to a materials problem. So there's this great physicist. All his life he says, "I'm going to devote myself to fusion business. It's so important." And they said, "But is it going to happen in your lifetime?" He said, "Not in my lifetime, but if it works, it's really important." He dies. Gates of heaven. He's St. Peter. I need to speak to God. Very important. Normally this isn't done. But for you, you're such a good human being, we will make an exception. He goes before God, and he says, "God, all my life, as you know, I worked on fusion. Will it become commercially successful?" God thinks about it and says, "Maybe so, but not in my lifetime."
I'm tempted to stop at that point. However, we have one last question which has been received several upvotes. Stephen will end on this one, and it's back to that circular piece around technology, policy and economics. Having worked in government and having served your country, arguably the world community so well, do you have any thoughts on how to avoid the politicization of climate change solutions?
I have very clear thoughts about that, but but you need some leadership, and that is, you need serious practicing scientists at the highest levels of government. Thatcher and Merkel were scientists, but practicing scientists. Why? Because they can call on the phone and call people into government service. And so Obama didn't know me. I didn't do politics. And yet he wanted me to be a Secretary of Energy. But that was an exceptional president. I think as voters, you should tell your politicians that you need a few scientists at the big table, at the budget table, at the policy-making table. And that is so important. And because they could begin to see how these decisions are made and what would be economically better to make shaky money. You want to make fossil energy a stone by technology and science.
I think we can all agree with our guest speaker on that last point. So, fellows, ladies and gentlemen, guests, we've run out of another very precious resource, and that's time for our guest speaker tonight. I want to thank Steve for being so generous with his time, his thoughts, and the energy that you've driven him into the room. And you can see, of course, why Steve is still a heavily sought after voice of reason and expertise. His unrivaled experience and vision, I think, is still absolutely apt, and we'll use this speech in particular, Steve, to inspire us as an academy to redouble our efforts in this space. So thank you for everyone who've joined us online, of course, and everyone here in the room with us. And please, of course, look out for the Academy's next big project, which is just round the corner, and that's the launch of our National Engineering Policy Centre manifesto, which will be released in Parliament next month, where we will set out, on behalf of the Academy and our profession, the engineering profession's key priorities for the next government, whatever shape or hue that might be. Engineering and science at the heart of it has to be one of our great focus points. So let me conclude for all our friends on the online community, and for those in the room, we're now going to go next door for some refreshments, and let's again, ladies and gentlemen, give a very big vote of thanks to our guest speaker.